Hi everyone, this is Mrs. J, and today we're going to be finding rational solutions of polynomial equations. Alright, I have a quick warm-up for you guys, so if you could pause the video and give these a try, we can check your answers in just a few seconds. Alright, so go ahead and check your work here. Part A, you can factor using magic x, so you get x plus 14 times x minus 2. For part B, you need to use that grouping method because our A value is greater than 1. So you multiply A and C to get 15, and then you ask yourself what multiplies to make 15 and adds to make negative 16. So we get negative 15 and 1. And we're going to put negative 15 x next to the 3x squared because they have a common factor. So remember, we're essentially just rewriting negative 16x as negative 15x minus x. So just writing it as two separate terms. And then from here it's factor by grouping. So factor out a GCF, and if you end up with the same factor twice, you can group the coefficients. So that's exactly what we did in part C. Remember, anytime you have four terms, you should always try to factor by grouping, and in this case you can. So again, factor out a GCF from the first two and then the second two. And if the factors match, you can group the coefficients. So when we're solving polynomial equations, our first goal is to try to put our polynomial p of x into factored form. If we can factor it completely, that allows us to find all of the rational zeros. So we learned a lot of different methods for factoring. But what if we come across a polynomial that cannot be factored using one of the methods we learned? We need a starting place. So that starting place is called the rational zero theorem, or some people call it the rational root theorem. So this theorem says if p of x is a polynomial that has rational zeros, so it is important to note that some polynomials don't have rational zeros. But if they do, then we can always find them using this formula m over n, where m is a factor of our constant, which is the no variable term, and n is a factor of the leading coefficient. So the answer will be somewhere within this long list of numbers that we're going to create using m over n. And then once we have our list of potential answers, all we need to do is start checking them until we find one that works. So again, this m over n is going to help us get a starting place. So we're going to start by simply listing out the possible rational roots for the following polynomials. We're not going to check them and we're not going to solve them. We're just going to practice using that m over n. So here I have x to the fourth minus 3x cubed plus 2x minus 16. So you could try to factor this. It is not factorable how it is, so we need that starting place. So first we need to figure out what are all the possible factors of our constant, which is negative 16. So those are going to be our m values. And don't worry about that negative actually, because we're going to use plus or minus for all of these values. So we have plus or minus, and we're going to list out all of the factors of 16. So that gives us 1, 2, 4, 8, and 16. And all of those are plus or minus. And then we need to list out all of the potential n values, which are all of the factors of our leading coefficient, which in this case is 1. So there's only one factor of 1, maybe plus or minus 1. So now we need to create all of the possible combinations of m over n. So all of these again will be plus or minus. So we do 1 over 1, which is 1. Then we have 2 over 1, 4 over 1, 8 over 1, and 16 over 1. So this is saying that if this polynomial has rational zeros, it will be one of these numbers. And just note that there are actually 10 options here. So there's 5 positives and 5 negatives. So you have 10 potential options to find a rational zero. Okay, let's look at example B, and again, we're just listing out the possible rational roots. So let's start by listing out our m values, which would be all of the possible factors of 10. So 1, 2, 5, and 10. And then we'll do our n values, which are all the possible factors of that leading coefficient. So 1 or 2. So now we have to find a way to show all of the possible combinations of m over n. So I'm going to do first all of these m values over 1. So that gives us plus or minus 1 over 1, 2 over 1, 5 over 1, 10 over 1. And then we'll do the same thing. We'll do all of those m values over 2. So that gives us 1 over 2. Now if I do 2 over 2, that simplifies to 1, so we already have it. And then we have 5 over 2. That's a new one. And if we do 10 over 2, that simplifies to 5, so we already have it. So here you can see we have 1, 2, 3, 4, 5, 6, but with the plus or minus, we actually have 12 potential rational roots. So again, that rational zero theorem gives us a starting point to hopefully help us find one of our rational roots if they exist. So now that we know how to list out the potential roots of a problem, let's actually give one of these a try. So here we're asked to find all the rational roots of this function. Of course, you should try to factor it first. You could try to factor by grouping, but it doesn't work. So that's when we know we need to use that rational zero theorem. So first, let's list out all of the m values, which would be all of the factors of negative 20. So 1, 2, 4, 5, 10, and 20. And then we're going to list out all of the potential factors of our leading coefficient, which is just 1. So this gives us a list of numbers to try. So we're going to do all of these over 1. So plus or minus 1, 2, 4, 5, 10, or 20. So we actually have 1, 2, 3, 4, 5, 6. And with the plus or minus, that gives us 12 options. So now we need to start going through the process of checking these until we find one that works. So unfortunately, there's no quicker way to do this. We kind of just need to plug through it. And the way we're going to check these numbers is using synthetic division. So it's really important that you get comfortable with synthetic division. So we're going to just kind of go through and start testing them. When we're doing the synthetic division, remember we set up the coefficients of our polynomial, so 1, 2, negative 19, and negative 20. And in the box, these are actually zeros, they're not factors, so whatever zero we want to try, that's the number that goes in the box. So say we want to try positive 1, we're going to put positive 1 into the box. And we will know if this is a 0 if we have a remainder of 0. So we're looking for synthetic division with a remainder of 0. So let's start our process. So drop the first number, and then we multiply and add, and then we multiply and add, and then multiply and add. So this has a remainder of negative 36. So 1 is not an option. Okay, so let's try another one. Let's say we try negative 1. So list out those same coefficients. So we multiply and add, multiply and add, multiply and add. So here, since we found a remainder of 0, that means that this is one of our answers. So this actually worked. Now, because negative 1 is the 0, I'm going to keep track up here. That means that the factor would be x plus 1. So our goal is to find the zeros, but we're first going to try to write our function in fully factored form. So we found one of our zeros, and we've actually reduced our polynomial down to this. So anytime you found an answer, we're going to look at what we have left, which would be x squared plus x minus 20. Remember, we always take the starting degree and we drop down 1 to find our what remains, and we're always going to see if this can be factored more. So for this, we actually can factor it. It's a trinomial that we can factor using magic x. So what multiplies to make negative 20 and adds to make 1, 5, and negative 4. So this becomes x plus 5 and x minus 4. So those are our last two factors. And a good idea that we're done factoring for these problems is if the degree is 3, we should end up with, we're trying to end up with 3 solutions, or we still want to have a degree of 3 once it's factored. So 1, 2, 3. So here's our fully factored function. And now that it has been fully factored, we can see from the factors that our zeros are negative 1, negative 5, and positive 4. So remember, the relationship between the factors and the zeros is they're always opposites. So you can see again that we use that rational zero theorem to give us a starting point to help us start testing to hopefully find a zero quickly. And then once we find one, we're hoping that the remaining polynomial can be factored by hand so we can find the rest of our solutions. All right, let's try another one together. So here we have this new polynomial. It cannot be factored. We don't know any methods for factoring with 5 terms. So that means we will need to use that rational zero theorem to help us get a starting point. So let's start by listing out all of our m values, which are going to be all of the factors of our constant, the 24. So 1, 2, 3, 4, 6, 8, 12, and 24. And then we'll list out all of our n values, which are all of the factors of our leading coefficient, which is 1. So for those m over n's, I'll write them under here. It's all of the possible combinations of your m's over your n. So plus or minus 1, 2, 3, 4, 6, 8, 12, 24. So we actually have quite a few options to pick because remember, each of these are plus or minus. So when you're picking, I mean, it's best to try to use a little bit of logic or a little bit of common sense of what you're picking. We can probably guess that these super large numbers are not going to work, so I usually will start with the smaller numbers. But again, you really can pick wherever you want to start. So let's say we start by trying positive 2. So list out the coefficients. We're going to use synthetic division. So 1, negative 4, negative 7, 22, and 24. So we multiply and add, multiply and add, multiply, add, multiply, add. So since the remainder is not 0, we know that negative or positive 2 is not one of our solutions. All right, let's try something else. Let's try negative 2. Okay. So when we multiply and then we add going down, multiply, add going down, multiply, add going down, and then multiply and add, we see that the remainder is 0, which means that negative 2 is one of our rational roots. So we've found our first root, which we can turn into our first factor, which would be x plus 2. Remember, if the 0 is negative 2, the factor will be x plus 2. So now we have to look at what remains to see if we can factor it more. So we have x cubed minus 6x squared plus 5x plus 12. So here we could try to factor this using by grouping. But I think you would quickly find out that we cannot factor this by grouping. So that means, unfortunately, that we have to start over and we have to do the rational root theorem again, but from this new reduced polynomial. So at least we have something a little bit smaller to work with. So I'm going to rewrite this up here. So here's what we're working with now. We have x cubed minus 6x squared plus 5x plus 12. So when we use the rational zero theorem again to find a new starting point, we want to start with all of the factors of our constant, which is 12. So I'm going to reuse this list and just cross off the ones that don't work. So it would be 1, 2, 3, 4, 6, 8 doesn't work, and 12 doesn't work. So it narrows down our list a little bit. But again, we just need to start guessing and trying new numbers in this new reduced function. I also want to point out that just because -2 was one of our solutions doesn't mean that it's out of the running. It can be a solution again. It could be like a double or a triple root, so it doesn't mean you shouldn't try it. Okay, so let's look back to here and let's try another one. So let's just start with +1. And again, we're not going to use these original coefficients because we have a more reduced function, so we'll use these new coefficients. So we multiply and we add, we multiply and we add, and we multiply and we add. Okay, so +1 doesn't work. Let's try -1. So when we multiply and then we add, multiply, and then we add, multiply, and add, we get that remainder 0, which means that -1 is a 0, which means that the factor would be x plus 1. And now let's look at what we have left over, and hopefully we can factor that by hand. So again, we started with x cubed, so that leaves us with x squared. And actually, as soon as you get to a quadratic equation like this, whether it's factorable or not, we should be able to solve, because we should know how to solve any quadratic equation. So this quadratic expression is factorable. So what multiplies to make 12 and adds to make -7, we can do -4 and -3. So those are our last two factors, x minus 4 and x minus 3. And then remember, if these are our factors, then that means that our zeros, let me zoom out just a little bit more, would be x equals -2, -1, +4, and +3. So remember, the zeros are always opposite of what you see in the factors. Alright, so I have one for you to try on your own, so please pause the video and give it a try. And when you're ready to check, or if you get stuck, just hit play to see the solution. Alright, so go ahead and check. So this polynomial is not factorable, so we need to use that rational zero theorem. Luckily, with the m over n values, it only gives us 8 potential options, so there's not that many to try. So the first one that I found that worked was -1. So you can see, because my remainder was 0. So this 0 gave me a factor of x plus 1. And the remaining polynomial, x squared plus 2x minus 15, we can factor using magic x. So that gives us the last two factors, x plus 5 and x minus 3. So if these are our factors, our zeros are -1, -5, and 3. Alright, I have one last problem for you to try. So go ahead and try it on your own. And again, when you're ready to check, just hit play. Alright, let's go ahead and check your work here. So you can see here I listed out my m and my n values, and here's all of the potential combinations. So I did my m's over 1, and then my m's over 2, and then my m's over 3, and then my m's over 6. Just beware, like when I do 2 over 2, it's equal to 1, so that repeats. Same for 2 over 6 is 1/3, so it repeats, so we don't need to write it again. So I started checking. The first 0 that I found that works was positive 2. So that gave me the factor x minus 2. And then that remaining trinomial, 6x squared plus 5x plus 1, is actually factorable. So I used that grouping method, and I got the two factors, 3x plus 1 times 2x plus 1. So if you did zero product property here, I know it's a little bit trickier just to say opposite, but if you took, say, this factor, 3x plus 1, and you set it equal to 0, you get 3x equals negative 1, and x equals negative 1/3. Same for that 2x minus 1. So we're really just doing zero product property, which is why it's always the opposite value that we see. And there you have it. Alright, so I know that these types of problems can be very tedious, but the more you do them, the quicker you'll get at synthetic division, the better you'll get at factoring. So just stick with them and don't give up until you find the zeros that work. Alright, that's all for today's video. Thank you so much for watching.